thought it was an easy exam, which I just didn't get because I was out of it. But it turns out I was out of it and also a challenge, so it's okay.
Is there a reason outside?
Well, I guess
Because there might be.
How do you go about doing that task?
These are my two choices. It is this,
One day.
so much shit to do for her.
Imagine you're doing it. I'm doing two physics. Well, I've been good at that. After that exam, I just didn't do anything that I tried to think about. So I helped how I did. I should have done something like a decent. I only did one thing because I should have done.
Oh, wait, I get it.
I mean, I also
You should be able to recognize.
Well, like, obviously, your base usually
No, PC is still broken. I mean, this week is just
yeah. I mean, yeah, we should go.
I didn't mean to look over your shoulder, but whatever that thing was, it's like
When you guys have to like advise you in
I have meeting exceptions.
Like,
I wasn't trying to look over, but like I glanced and it was so shiny that like it stood out to me. I was like, wait, that's shiny.
like it's random.
Yeah, where?
go into options. Yeah, user settings and it just like pops like.
Really, I don't.
Oh wait, refresh the page and look at the bottom right. It's like, because like I was
Oh yeah, no, I think. Wait, what?
that's easy.
How many times have
I guess so many times.
Oh, this is
Yeah, but I'm about to hurry.
Yeah, it's not long.
I don't think she'll care better.
That's true.
She gives a lot of easy words.
It's also really fun, but I
may not understand the irony.
it doesn't matter what
I kind of like, I optimize it to that.
Yeah, I do feel that. I do feel that.
Bro, it's maybe
You're right, you're actually probably like,
I heard you did it.
I checked out where
and so maybe it's like
I'm meeting with her today. With Lance.
I can do this, and it's like, bro, I can see my screen.
they don't do it really.
The iron like half. It's a ramp.
No, we look at, I looked at my classes where it's like, we're telling the class, we're looking at the
It was great. It was just like reading it, just like maximizing
legally. It's first joy, I promise. For me, the one class I have to take.
Don't look at the cat.
Not
To the ramp.
don't want to, but I have to. I just kind of want to.
No, it's the ramp file.
All right, I have juggled our syllabus a little bit. Starting my recording now. I did not send you notes for today, so I don't have timestamps. If you could just write the titles down with timestamps, that'd be rad. But yeah, I decided I'm going to juggle around the syllabus a little bit to get us into heaps a little earlier. And then, because I'm not quite sure how long it's going to take us to work through them. And I want to make sure that you have requisite knowledge for when the labs show up on the syllabus, because I don't want to change the lab dates, because we'll schedule around them. And so then the last part of the class, I'll go into some ancillary topics. First thing I want to talk about today, though, is one of the questions on the midterm that a lot of people got wrong, but you should have got. It would have been easier if we had done the ASLR class before. So one of the questions on the midterm was why do we return to code pages and not stack or heap pages? And a lot of people said, well, ASLR moves the stack around. That's true but irrelevant. Okay, here's the thing. ASLR moves everything around. A good implementation moves everything, right? So that makes everything equal in the eyes of ASLR as far as what's the best thing to return to. Here's the difference. A code page never moves relative to its base address. That's the address that ASLR assigns to the thing that gets loaded, right? Your stack moves relative to its base address based on the state of the system. Your heap, where things are on the heap, move relative to its base address. Okay, and we're going to talk about why that is today. But does that make sense to everybody, right? ASLR means everything moves. It means you need a peak to do anything at all. Even without ASLR, the stack and heap will move. If you have a peak, you still can't rely on your stack address. What you can do is rely on relative stack addresses. Stack frames tend to all look the same, especially if you don't use a lookup, which some of you have discovered. Okay, that is a function that basically inlines sub-ESP some number. It means you can make dynamic space on the stack. You should never do that. Giving your user control over how big your stack frame gets is a big mistake. Okay? In the kernel, you definitely won't be able to do that because there's a very small fixed stack size. It's like 2 or 3 pages per thread, and you get to the end of that, and the whole thing explodes. You're not allowed to do that. You should never use recursion in the kernel either. You want to have strong control over these things. Okay? But yeah, let's talk about dynamic memory use. Okay? You can build a program that just uses static memory. Every old video game system you've ever plugged in works that way, right? Like if you turn on a Nintendo Entertainment System, there are fixed pages. Like your dynamic memory is this one page. You get 4096 bytes to work with, period. That's it, okay? And that's all you get. Virtual memory, however, on modern systems means that we can grow or shrink that space, generally just grow and not shrink, to get the memory we need for dynamic programs, right? If we want a program that's going to respond to the types of inputs a user provides, it needs to be more flexible than having static local variables, right? So this is all handled in user space, okay? Our kernel provides memory to user space in a really stupid way, okay? It's one of 2 ways. The first way is when we start this program, the loader provides us kind of a very small heap. Let's say it's 1 page, just for ha-has. And so it has a start address. Start. When I draw the heap, I draw it sideways, and you'll see why when I start building bigger data structures. But so this will be +0, and this is +1k, right? And so our heap in this place, let's say our base address is 0, and so our end is here at 1k. We could call the system call brk with 2k, and that would give us another page. Now end is here. And that is all brk allows us to do. Okay? It takes an address, and it says, can I provide you enough pages to go from where I'm at to the address you gave me? Is there stuff in the way? If not, okay, I'm going to give you those pages, provided you have enough virtual memory to satisfy this, right? That's all brk does. User space programs got to deal with that on its own, okay? The other way that this can work is mmap. And if you use mmap, some of you may have looked at nmap already for some of the other assignments. Mmap gives you a lot more control, okay? mmap allows me to say, I want to have pages that go from this start address of this size, so I can ask for as many pages as I like. I can decide where they get mapped in memory, or I can say map it anywhere and just hand me back a pointer to it, and I'll have 2 pages. Okay? I can ask mmap to provide me anonymous pages, which means that they are just virtual memory backed, just like BRK. It's just going to hand me pages from RAM that's been zeroed. Or I can ask it to back it with a file, right? So I can map into memory directly from disk, and then I can provide it options to say, oh, I want that cached from disk, so that it's not automatically written. The kernel will decide when to write that to disk. Or I can have it be directly mapped, where every time I make a change, it gets directed to disk, and everybody who's looking at it gets to see it. We use the shared memory. But those are the only 2 ways that the kernel can hand us memory. Everything else here is handled in user space. Okay? So if you write an assembly program and you don't load any libraries, and you need heap space, you got to do all this stuff yourself, okay? So generally, in old school computing, you're just handed those pages and you just work with them, right? When you get into virtual memory space, which is a little bit newer for non-Unix people, we have Doug Lee comes to help us out. I don't know where he got those glasses, but I'd love a pair. I think I would look very professional in them. All of the modern inline heaps are based on his implementation, okay? So we're going to look at, in the class, 2 types of implementations of heaps, okay? The first one is all of the information about the heap is stored in the memory itself that you get access to. And then the second type, all of the metadata for the memory that you have access to is stored someplace else. There are pros and cons to each of these approaches. And we are going to start with kind of the simplest implementation of this method first and kind of build our way up, okay? Now, in a side here for object-oriented people, we are not talking about garbage collection. Garbage collection is something that sits on top of these things. Okay? It is a complication beyond what we're talking about today. Anytime you have garbage collection, you also have all of this type of stuff. If you have this type of stuff, it doesn't mean you have garbage collection. Okay? When we get into talking about the types of bugs that you see in heaps, we will talk a little bit more about garbage collection and garbage collected languages. C and C++ are not garbage collected. Putting aside, Windows kernel is garbage collected, but that is built on top of C++. It is specific to the kernel, okay? All right, so when we talk about objects in the heap, we are talking about heap chunks. That's what they are called, and the chunk contains not just what is returned back to you when you call malloc, it also contains a header that sits behind that pointer. Is everybody comfortable with using malloc and new to get space? Do you understand what happens when you make those calls? Some people I know don't. Okay? So what is happening when you call malloc is it provides you a pointer to space, and you may use that however you like. Okay, that pointer is within the virtual memory of your process. If you have a threaded process, it's probably shared. Some is not, but mostly it is by default. But what you are getting is a piece of memory in one of the pages that the kernel has provided to us. So let's give ourselves a big ol' heap chunk here, and we'll say that's 2 pages. So this is +0, +1k. I'm going to do plus k instead of putting in all the zeros plus 2k, and that's all in hex, right? So 1k hex is 4096 bytes. That's one page. One page is always that much, even on a 64-bit system, okay? And so when you ask malloc for something and it hands you back a pointer, it's handing you a pointer to the middle of a chunk, okay? And a chunk header in our implementation that we're going to be talking about here, inline data, has a couple of pieces of information that are necessary for the system to work with that chunk, okay? And so it's got here a, let's say the header looks like this. I'll break it up here into kind of three pieces. So it's got a previous size. That's the first thing it's got. It's got my size, the size of the chunk in question. And then the low order bits of my size generally have some flags. And the most important one there is in use. Okay, so is that chunk free? Or is that chunk being used by the program itself? Okay. With this information right here, we can do basically everything we need to do for a baseline heap implementation. Okay. Now, having the prev size and my size, just those two things basically provide you the functionalities of a linked list, a doubly linked list, in fact, right? The metadata being in place means that you need to store less data to have a linked list functionality, okay? From here, if I have a pointer to my chunk, I know where the last chunk is, right? It's this pointer minus the previous size. That gives me the one previous. If I want the next one, what do I need to do?
Add my size.
Add my size, right? Pointer plus my size gives me the next chunk, okay? And then in use says,
just to be clear, does my size and previous size contain the header size?
yes, it does. Yep. Yeah, it does. It doesn't necessarily need to, because you could do the math yourself, but it generally does in all of the implementations I can think of off the top of my head right now while we're talking. Here's the other thing. The reason that I am teaching this in this kind of vague way, where I'm saying, you know, here is an implementation, is that all of these things are implementation specific. It's part generally of your libc. So NTDLL on Windows will handle it. glibc on Unix will handle it. But very, very many programs bring their own custom compiler. Sorry, not custom compiler, custom allocator, right? These solutions are optimal for certain thresholds of use in certain ways. I'll talk about that a little bit later. But a lot of times, if you are using or writing a program that needs to act optimally in a certain situation and you know what that optimal situation is, you'll pick an allocator that caters to it, okay? Which means that my web browser has a different allocator than my PDF reader, which has a different allocator than my my JavaScript JIT, which has a different allocator from my video player, right? You can generally know what that is, because at compile time, it'll load something up and generally doesn't change from that. But that's one of the reasons that we are going to talk about how the allocator works, but we're not going to spend a lot of time attacking the allocator itself, right? In real life, if you memorize how one particular allocator works in specific without understanding why it works the way it does, as soon as you move on to another program, it's not going to be applicable, right? So your goal here is to understand what choices were made to build this thing, what goals they serve, and then what it's good and bad at and what the implications are, right? So one of the grad readings that I'm going to hand out after this class is going to be the Malik Maleficarum paper. And I don't want you to memorize the paper. What I want you to do is ask yourself a couple questions about it. And the questions are going to be, why does the allocator have this piece of functionality? What does it serve? And then what can I do if I control different pieces of memory within the allocator given that structure, right? And you will use that in a general way. The name of the game for good hackers is generalization. It's not learning rote solutions to problems, because problems are always implementation specific. It's learning the types of things you can do with the types of solutions people commonly use. I actually also was thinking a lot about why I dislike people relying on CTFs so much. And the answer that I came up with was very similar to that, which is the reason people get stuck doing toy problems and not moving into real life problems is that understanding real life problems is about recognizing the common solutions to common problems and then being able to make use of those. And toy problems don't have the pieces, the Lego pieces that real programs have. And so when you start looking at real programs, one, you're lost because you don't understand the Lego pieces. And two, you don't recognize, let's say, the opportunities you have for manipulation because of that, right? So getting into real programs as fast as possible, real implementations, is super important. You are machine learning your own brain with implementation examples, and you want to get into that as fast as possible, right? Yeah, okay, so some things about this. In the implementation that we're going to talk about today, which comes out of my brain, each one of these is going to be 4 bytes, right? And that, all of this is 4 bytes, this is 4 bytes. So the header size is, sorry, this is 4 and this is 4. Oh, 8, thank you, there we go, 4. 8 size, right? So we're going to be able to give ourselves kind of a limitation here on this thing, and we're going to say chunks have a minimum size of header size times 2. If I can ask for a chunk that's 9 bytes, then I've wasted 8 bytes of overhead for a 1 byte chunk. That's not going to be great for me, right? And that gives us an opportunity to use the low order bits for my size as the in-use flag and some other flags, right? If the smallest increment that I can make is 16 bytes, then I don't need the low order bits of my size. I can assume the low order bits of my size are going to be aligned, which means I can use those bits for other things. Does that make sense? This is a common technique in systems programming where you say, because I have a threshold size for my object, right? A lot of the times it's going to be powers of 2. I don't need nearly as many bits to get to 4 gig, right? Especially if I'm using buckets of powers of 2, which we'll see later in this implementation. 1 is equal to my minimal bucket size, which in this case is 16. And so 2 is equal to 32, and 3 is equal to 64, right? And so in order to get to 4 gig, I get a lot of extra space to use for metadata, flags. In this case, we're just going to say our flags are in use. There are other flags, but this is the most important one for you to understand. The rest of them are not super important for our understanding right now. Okay? When I call malloc, I get a pointer back. Now, the allocator knows the chunk starts here, but when you get a pointer, you get the pointer at the end of the header. Okay? So if you call malloc in an implementation like this, one of the inline ones, and then you subtract 8 from that pointer and you look at it, you'll see your metadata. Okay? But when you're handed that pointer, it is after the header, which means you can use that memory directly, right? You don't have to walk forward 8 bytes so you don't trash your own header before you start writing. It looks like you just get this free memory, right? So that's a chunk. When we perform allocations with this chunk, we go through a pretty simple algorithm in the base case. Okay, so before we solve any of our optimization problems, we've got kind of a simple algorithm. And the algorithm is, you start at the start of the heap, or the allocator does, so glibc, in your case, will start there. And it'll walk, check the header and say, okay, I want 32 bytes. Is the first chunk I'm looking at, is the in-use bit set? Okay, if it's not set, then it's free, we can use it. Okay, second question we ask is this free chunk large enough to service the request we've made? Okay. Now, if it is bigger than what we want, plus the minimum size of 16, it'll cut the chunk. Okay, it'll make a cut here, it'll change my size to be what we asked for, it'll stick another header here. Okay, and it'll hand us back that pointer there. Okay. If not, it'll walk to the next one, check it's in use, check its size, and go on. Okay? So this cutting means that even though we're getting a page at a time, we can ask for chunks that are smaller than that without wasting a bunch of memory, right? So as we go, our quote-unquote inline linked list here will just add more elements. Even though we're not adding more memory, we're cutting the size, right? So now we have an allocator that works, okay? It's got some problems in terms of optimization that we're going to address in a second. But if you have this with that algorithm and those chunk headers, you can have an allocator, right? It'll service the program. It'll give you chunks when you need it. You're going to have to come up with some way to free it back if you want to be able to do that. But this is enough, okay?
I'm confused on the part where you said that pages are split into chunks, and now we go about like going through those chunks. What if we go and like we need to go on another page, like in chunks? How those chunks connected in one page, from one page to another?
So when we are asking the kernel, either through BRK or mmap to give us pages, we ask for them in contiguous space, right? So BRK will always give us continuous pages in virtual memory, because we're saying, here's where it starts, I want it to end here now, everything's contiguous. I'm asking for it with mmap. It's incumbent on the allocator itself to be like, I want a page right here, the next page, right? And so they're always going to be contiguous, okay? So it doesn't matter if a chunk goes past a page based on its size, that's fine. Does that make sense? Yeah. Does anybody else have any questions about the minimal viable allocator? You will not see an allocator that is simpler than that.
What if you're like, your current chunk is just a little bit bigger that you can't fit a new header into after you split it?
So it will only split if it's worth splitting so that the space left over is our minimum space. Otherwise, it will be unused, right? So sometimes you will have allocations that don't abut another allocation directly, right? Anytime you ask for a size that's not within a power of, not a multiple of 16 bytes, you're going to have extra space that's just left over, which means that if you have an off by one, it's probably not going to hit anything useful, right? So maybe you have like 15 bytes of leeway for you to be a sloppy programmer, basically, right? If it can't cut it and there's nothing left, it's going to get a new page and put your chunk there, right? So, yeah. So that's why we say here our static header plus the size to allocate plus the minimum size for the chunk, which is 16 bytes. If it's not, it won't cut it. Okay. So first problem is finding a free chunk. If we want to find a free chunk in this, we've got to traverse all of the memory. We start at the beginning of the heap, we walk the whole thing. Some of them are free, some of the chunks are not free, right? So we also have trouble with getting memory back in this scenario. So the first complication that we're going to add to this is a linked list that lives inside there. You ask a question? Yeah, what's up?
When in the basic allocator, is the initial chunk the actual size of the entire keep the initial heap size.
Yep, yeah. It'll be the full size, and then when you start using it, it'll start getting cut, right? So you only have one element in your quote-unquote list at that point. One other thing here. We are now going to add a secondary linked list into this linked list, okay? Our first linked list doesn't necessarily look like a linked list, but it is a linked list in the way that a vector acts as a linked list, which is, yeah, it's contiguous memory, just like an array, but we are going to walk through it as though it is a linked list, right? So our next complication here is that we are going to do something when a chunk is not in use. When a chunk is free, we are going to add another header, which is going to be a free header. And that's going to take up another 8 bytes. So it's going to be another 8. And it's going to have a prev pointer and a next. Well, actually, it's going to be a next and a prev. Next and prev. And we're going to keep a free head pointer someplace else. Okay, so in our keep header, which contains how many pages we have and some other profiling data, we're also going to keep a free pointer, which is a pointer to the head of our list. So now, when we want to allocate a chunk, we're not going to walk everything. We're just going to walk the list of free things. Okay? And from here, we'll subtract 8, and we can check the my size and do all the previous algorithm work that we had done. So we've got now 2 linked lists that are maintaining information about the same chunk of memory, and they live inside that chunk of memory. Okay? We're also going to make it a doubly linked list for a specific reason. You asked the question, Stefan did, last week, if we trash the pointers in the linked list, how do we get to the chunk that's there? This is how. We are not necessarily relying on that free linked list to keep track of all this memory. We have track of it. We know it's in the pages. We have pointers to it in user space. We're using this linked list to facilitate us working with this memory, not to necessarily store where it is. And this happens very often. You will see a lot of system structures that have a lot of data in them, and then a linked list header in the middle, or maybe 2 or 3 linked list headers in the middle. And what they are doing is allowing schedulers and other programs, other threads in the kernel or wherever to say, I want to see all of the processes that are within this state right now. All the processes that are waiting to be run, it's in the list. Okay? Once I run one of them, I want to take it out of the list. That doesn't mean that object goes away. That means it's no longer within that particular list. Right? Looking at people's heap implementations, and when you're taught generally, the way that you're taught a linked list is this is a way for you to store multiple pieces of memory if you don't know how big they're going to be. It is not taught this is a way for you to keep track of objects that may or may not be in a certain state, right? So very often we're not going to say, I'm going to walk the whole list. We're going to say, I have a pointer to this. I need to remove it from a list that someone else is looking at. So in this case, this chunk is in the free list because it's free. We go to use the chunk, okay? We set the in-use flag, we cut it if necessary. This header is no longer valid, and that's no longer a free chunk, so it doesn't live in the free list anymore. We have to remove it from the free list, okay? We didn't walk the list to get to that pointer, necessarily, but it's got to be removed from the list, okay? And a doubly linked facilitates that. Why is that? Hold on.
You can get to the previous and next using that sign.
in constant time, right?
So if you were to, I guess, split a chunk, like you're allocating less than the size of the chunk, in this case, would you also have to make a new node that's free, that's smaller?
Yes.
Okay.
And you add that to the free list, right?
Okay.
That's another reason that you have to be a multiple of the header size, because it's got to have space to store that free header. If it's 16 bytes, all of this here becomes your next chunk, right? And then you add that next one in. So you remove the first one, cut it, add the second one, right? That's part of your use. What was I saying before that? I had asked the question, why doubly linked? Yes, so the answer was, in case people didn't catch it, is I can remove it from the list without walking the whole list. If I have a singly linked list, and I care about the ordering of that singly linked list, and I care about picking a particular thing out of it, I've got to start at the beginning and walk to find the previous one so I can link past it and remove that piece. With a doubly linked list, I don't have to traverse the whole list to remove it. If I have the pointer, I know the last one, I know the next one, I can just pull it right out, right? So I go from end time to constant time. A lot of the stuff that we're doing here with having these multiple lists is moving from end time to constant time in allocation and freeing, right? All of these optimizations that we talk about are going to do that in some way. So it's going to isolate a situation that is common, turn it from end time to constant time. Make sense? One of the most important parts, if you are doing cloud computing, is turning end time to constant time whenever you possibly can. Because on normal computation, very often nowadays it doesn't exactly matter how much time you spend in the allocator. In cloud computing, almost all of your time is spent in the allocator, and all of that time costs money. And so if you want to save money, removing allocator time does that. But you notice, the more that we optimize, the more complicated this stuff gets, right? It started fairly simple. There's only one header. Now we've got two. We solved our problem of finding free chunks in constant time. Cool. Now we have another problem. The problem is fragmentation. Does anybody remember when you used to defragment a hard drive? Is that, yeah? You guys understand why that happens? Yeah? Same thing happens with virtual memory on the heap. If we keep cutting the chunks smaller and smaller, then what happens is we need to, anytime we want a larger chunk, we got to get another page. And so the virtual memory space grows and grows and grows, right? So we are going to do some work to consolidate our free chunks back together. And what that means is, when we free a chunk, we want to look at the chunks on either side, right? And we say if either one of those is free, or both of them are free, we're going to take all that memory and put it back together into one big chunk, which means we're going to remove one or two things from the free list, we're going to change the size header, and then we're going to go on with our lives with one bigger chunk where there were three smaller ones previously, okay? In this case, this is known as chunk consolidation. It is not garbage collection. The difference there is pretty large, but you'll see it as consolidation if you're looking up allocators in general. Okay.
Are there like any implementations that like consolidate them if they're not adjacent, or do they always have to be adjacent?
No, because that would be expensive. Here's why it's expensive. If I've got a chunk here and a chunk here and I want to put them together, I need to take the stuff that's in use in the middle and copy it someplace else. And then I need to zero out the other stuff, right? So you've got a mem copy in there. It's not worthwhile, right? Okay. Yeah. Okay, so in this case, we're going to be removing free chunks from the middle. We're going to unlink them using the algorithm that some of you have written But it's going to look like, let's see, chunk prev next is equal to chunk next, chunk next, prev is equal to chunk prev, and then you get rid of chunk. You don't actually need any temp variables to do this. And you don't need to walk the lists. It's very small and tight. It doesn't matter if there are nulls in there, except if your prev or next are null. In that case, you'll have to do some work, but otherwise, that's the simple case there for unlinking. When we get to the lab on owning our first heap, we are going to rely on that piece of functionality to do so. Okay? It is specific to this allocator at a specific date, but there is a reason that I like people to understand it. And that is because it is the first time that most people in hacking are going to encounter the idea of creating fake objects in memory to trick an algorithm. Okay? In order for us to own something where we have kind of corrupted this header data here, we're going to rely on creating a fake free chunk that doesn't exist in other states. And it's got all of the pieces of that fake chunk have to make sense in terms of the algorithm. So it requires a couple complicated things for you to understand. You have to take the heap, which is in an unknown state, and put it in a reliable state, which means manipulating it blindly. And then you have to be able to create an object that will jive with the algorithm that's working on it without crashing, which means you have to understand the object and all of the implications of the pieces of the header. And that usually takes some significant reverse engineering to do, right? I'm handing you this data here, specific to this allocator. If you come across something like this in the wild and you want to own it, you will have to do all the reverse engineering to figure out what the headers are, how they interact with that moving algorithm, and then how you can manipulate it, right? So I consider that task to be kind of a masterpiece for a beginner hacker. If you can do that task, then you will be able to continue on in hacking without hitting a wall in the foreseeable future, if that makes sense, right? That's like it forces you to do all of the advanced tricks that you will need to put together in the future. So it is worth learning to do if you want to go forward. I'm not going to give you that as an assignment in this class. It usually takes someone close to a month to do the first time they do it. It took Willow, who has some experience, 30 minutes to do the last homework that we gave, so homework 3, and 3 weeks to do that, right? Or did she not finish it?
Wait, homework 3?
She finished homework 3 in 30 minutes, right?
Oh, no, it was only 3 hours.
3 hours, okay, so 3 hours. She hasn't finished AV09, right? But
No, she did finish AV09, but that took a couple, weeks of audio.
Okay, so 3 hours for the last homework, several weeks to do this thing, okay? So I won't give it to you. We'll do it as a lab together. I'll give you a write-up on exactly how it works with diagrams, so you can take a look at it. That'll be homework for you to read. When we talk about owning the heap, we're going to look at working with the program itself and not with the allocator. But this is a good exercise for people to do if they want to move on to something more sophisticated. Okay. So if it is the year 2000, this is our heap allocator. Okay? So we've moved on from the simplest case to our case where we can defragment, and we've got a constant time allocation for our free list. Okay? Let's make allocation constant time too. This is the next optimization that you'll generally see, and any allocators that came between, say, 2000 and 2007 are going to have these optimizations, and they'll look basically like this. So if you're on Windows XP, if you're on any Linux kernel before 3 or 4, it'll look like this. And so the next thing we do is we add something that is called a look-aside list. You will see it in Linux referred to as fast bins or small bins, but the formal name of this optimization is a look-aside list. Okay, and many optimizations going forward on all heaps are going to rely on this sort of construction. And the question is what are we going to put in our look-aside list? How are we going to manage them? What are the restrictions going to be? But the look-aside list is the thing. And a look-aside list is a singly linked list, and generally you break it up by power of 2 bucket size. So what this is I've maintained everything else. This is all still here. I'm going to add something on top of it. And the thing that I'm going to add on top of it is, if I free a chunk, and it's a power of 2, and my free list is, my look-aside list isn't full, I'm going to add it to the head of my look-aside list for that bucket. So what we end up with is something that, let me give myself some more space here, shrink our heap back down. We end up with a set of singly linked lists that are size based. So this is 16, this is 32, this is 64. And I wrote those in decimal because I am a jerk. 10, 20, 30. Okay. If it is of size hex 10, plunk it right here. Okay, so what that means is it's constant time to free something, because I always put it at the head of the list. I use my singly linked list as a stack, right? That's another thing that I didn't see people do very often in their linked list implementation. People would walk to the end of the list and then stick their thing there. That's end time to add. You can always, because we don't care about the order of your linked list, just stick it at the head and push everything down 1. So you say, new node next is equal to head, head is equal to new node. 1 move, right? And so the last one we asked for, last one we freed, is also going to be the first one we get back. So we've added some reliability to the functionality of this thing in addition to optimizing. So does everybody understand kind of the optimization that we get here? When we're going to allocate 32 or 20 hex, we used to have to walk to find something that would satisfy that. In this case, we just go directly here. We say, is head null? If not, great, grab it. Head's now equal to head next.
Where is this getting stored for like this free bucket lists data structure?
It can either be stored in another header for the heap. So the heap itself will have a header that will store how many pages are currently there. It might store profiling data. So how often do I use a bucket of a certain size? Things like that for optimization later. It'll also store this. If you are looking at a more advanced heap, sometimes you will have a set of these for each thread in the program, so that now I don't have to lock the heap. I'll just say, per thread, I'm grabbing each one, right? So it depends. That's your basic answer there. That's where you're going to look for it. That's also what in PT malloc, which is the newer version of Doug Lee's malloc, what we're looking at right now. It is a direct descendant of Doug Lee malloc, and its optimization is per thread. It's got the look-aside lists. That's the thread cache, right? Yeah, so now we have constant time, add, remove for buckets of common sizes, right? And it gives us a little bit more reliability.
Those buckets won't be like actually next to each other in memory, right?
Nope.
Okay.
Yeah.
I feel like at some point during, maybe it was one of the grad lectures, you were talking about like knowing what size things would get allocated as, that way you knew which bucket it would be landing in.
Yep.
Is that in case you're able to like overwrite that linked list itself? Or I was thinking that was because you'd then like be able to overflow out of it and they're like, oh, the 32-bit bucket.
It's about the reliability of what I'm going to get. So here's the thing. Let's say I want to do a use after free, which means that I am relying on the allocator handing me back a certain pointer, right? If I know the last thing I freed at 10 bytes is the thing I want it to hand me back, I know it'll hand it to me back next.
Right, so you do a 10 byte out. Yeah, okay.
Because we always pull from and right to the head. So, first in, last out on this stack. So I know if I freed A, B, C, my next 3 allocations of that size are going to be CBA, right? Every time, very important here for advanced understanding, every time somebody adds an optimization like this, they have provided you control over how the thing works. This goes for every single algorithm in every single case. Have people looked at the branch prediction information leakages? Yeah? What's going on in branch prediction information leakage is that I've got an optimization and an algorithm. It can go in one of 2 directions. In a certain case, going left is more advantageous, and in a certain case, going right is advantageous. If I don't know what data is going through that algorithm, I can time it and say, if it took 2 seconds, it went left. If it took 3 seconds, it went right. Now I know something about the data that's going through there, okay? That's one way that you can take advantage of this. The other way that you could take advantage of this is if you're the one who gets to provide the data to the algorithm, you get to pick if it goes left or right. And there are different side effects of going left and right. Necessarily, if there were not, left and right would be exactly the same. There would be no reason to have a branch there. In this case, because of this structure here, I've gained some knowledge about what's going to happen, and I've gained some reliability. In the simple case of our heap, things are very random, right? I don't know what's been allocated last. I don't know who did it. Even if I'm the one who freed something, I can't guarantee that I'm going to get that chunk back anytime soon, right? I have no guarantees about what I'll get back from the allocator. In this case, I have guarantees. Their optimization gives me more control, right? This is a weird thing, but I learned it very viscerally working on stage fright. Stage fright was the video parsing bug on Android. And I did it on a bunch of operating systems and a bunch of allocators because that was the job. And I learned very quickly which ones were easier and which ones were harder, and they were not the ones that I expected. I expected the simpler allocator to be easier to own, and it was much harder because it was less reliable. The more advanced the allocator was, the more reliable it was in terms of how it functioned, which means I could make my exploit reliable, right? I could know what it was going to do before it did it, as opposed to hoping it did what I wanted it to do. Does everybody understand this optimization, why we add it, and how it helps in our optimization? If you do Apr01, and I can give you a binary to work on if you want. This would be extra credit. Honestly, I'd probably take it as a final project if somebody wanted to use that as a final project and they don't have one. This is what the allocator looks like. Okay, it's going to have look-aside lists added in. All right. You work with this for about 20 years. You get that from the first Linux implementations and base Unix implementations, and it stays that way until, I want to say, XPSP2 is where you first start to see people make significant changes to this. And the reason is because at a certain point, this is less efficient. So this has a low overhead in terms of wasted page space. It has a low overhead in terms of the data that we store. Every time we add one of these optimizations, we are trading memory footprint for CPU time, right? That is a common trade-off you can make in computer science. You can say, I will use more memory to give myself different ways to work with this data set that will turn things from end time to constant time, or log time to end time. But I need to get more pages mapped to do that, which means I am relying on computation being more useful to me than memory footprint, okay? And so that changes based on what the program is doing. There may be programs, even more advanced programs, for which this is the optimal solution. If you look at Windows in particular, Windows has got 2 allocators at least that it swaps between when you're using NTDLL as a base allocator. Under a certain threshold, when you first start a program, your allocator looks like this. It is keeping track of all of the allocations, how fast they're happening, how often its free lists are full, and how often they're not. And when it gets to certain inflection points, it says, all right, this is not working anymore. I'm switching over to a low fragmentation heap. Okay? That'll give me a bigger memory footprint up front, but over time, it'll be more efficient for memory usage. When that happens, it's switching over to the other type of heap where the metadata is not in line. Okay? What that means for you in practice is that you will never work with this heap on Windows because you have no idea what state the program you're owning is in. Which means the first thing you do when you're trying to own something on Windows on the heap is you force it into low fragmentation heap, right? Because when I start looking at it, I don't know which heap it's using. I can't force it to go back to the original heap, so I must force it forward. And I can know, based on the program, if I do these sets of steps, it will always force it into low fragmentation heap, right? I just make it allocate a certain amount. Now I know it's in low fragmentation heap. Now it's in a more known state, and I work with it there. So you never use this on Windows. Not unless the program you are owning you know has just been started. And even in that case, it's not always the best thing to do. Does that make sense?
So there is a version of Windows C that still has inline metadata.
Yep.
Interesting. I thought it was all out of line with UG.
Well, see, that's the thing. If you're going to own it, it might as well be.
Okay, sure.
The very first thing you do is you force it into that because you can't now, right?
Okay.
Yeah, so it might as well not have this as far as a hacker is concerned.
Okay, okay.
That's why everything you see is low fragmentation heap, low fragmentation heap. Okay. I mentioned a little bit earlier, PT-malloc comes directly from this. It's a direct descendant. It has just added optimizations for threading. That means sometimes threads will have their own heaps. I didn't mention this previously. When we are looking at this implementation here, we are assuming that there is one heap for a process, right? That's not necessarily the case. I can create multiple heaps for a process, and I can say this heap works on this specific thing. This heap works on this specific thing. Why would I want to do that? Well, one reason is that anytime there are multiple threads using one heap, I've got to lock the metadata every time so that they don't step on each other, right? We talked a little bit about time of check, time of use, and other race condition bugs when I talked about the history of exploitation, right? And I mentioned in a signal handler, you don't call syslog because syslog calls malloc. Well, a signal handler is being handled, unlike an exception handler, in the same thread. And then it's going to jump backwards afterwards. So you can corrupt, because you're holding your own locks, you can corrupt the heap in that way. If I want to work with multiple threads, I can give each thread its own heap, and then I don't have to lock anything, because I know, as long as I don't do something stupid like call syslog within a single handler, that I'm never going to step on my own toes, basically, right? If you go to look up the T cache, which is the thread cache in ptmalloc, it's just a structure per thread, and it's a bunch of these. That's all, right? When on non-Windows will you see non-ptmalloc? Well, every browser is going to use low fragmentation heap, JEmalloc, out of band style. We'll talk about that shortly. Not today, some other day. V8 and other JITs are going to use their own. Even certain services in Linux will use it. And they don't have a swapping algorithm like Windows does, but generally when you write your program, you profile it and you say, damn, this is not working out for me. I'm going to put in another allocator, okay? Because your allocator is part of libc, and because of the way that dynamic loading works, you can always load a library that implements malloc on top of your libc, and when you call malloc, it will call the other library instead of calling libc, right? And you can do that dynamically. You can do it statically. You can statically compile a program where your allocator is some other allocator. When I hand you a homework that's JEmalloc, I will have statically linked JEmalloc as a library inside your homework program, and then it will run the other allocator, right? So you can make that decision on your own as a developer. Do I have anything else specific? More slides. Yeah, so I have rejuggled our syllabus a little bit. I wanted to push the heap stuff earlier, and I wanted to do that so that we could kind of get into some homeworks on the heap. The homeworks that I give you on the heap are all going to use JEmalloc, and there are reasons for that. If we use an inline allocator like this, you can still attack the program, but there are caveats, okay? If I am attacking objects that live on the heap, and I'm using an allocator with inline metadata, very often, in an overflow situation, I'll have trashed that metadata, right? Which means that if somebody walks the list or makes use of the chunk, the thing will crash, okay? So that limits us in terms of what kind of problems I can give you, but it's still possible to do. In real life, a lot of your work with heaps involves you understanding exactly how the program works with the heap, and either allowing it to do things that are advantageous or not allowing it to do things that are disadvantageous, right? And one of those things is, don't let it work with the chunks that I've corrupted until I have a chance to fix them. So I'll get execution, get arbitrary execution, and then I have to go fix the heap. And there are a number of ways to do that. You can understand it and understand the layout and fix it manually, probably the worst way. You can just remove chunks from all the lists, right? So that when anybody walks it, they just walk right over your piece. That's a really good way to do it, in which case you are leaking memory, which means that memory will never get used again by the program. It'll permanently enlarge the space of the program, but no one's going to catch you doing it. You can completely get a new heap, right? I said that there are ways to make new heaps. You can have multiple heaps per program. One of the things, if you totally trash your heap, is you say, all right, I'm never going to touch the objects that I used to create this broken page, and I'm going to just ask the allocator for a whole new heap, and then I'm going to point all the metadata at the new heap and we're just not even going to talk about that other one anymore. As long as nobody touches it, it's not going to be a problem, right? And that's totally doable. Like that's a strategy I've used before. In some cases, if a genius looks at your memory dump, they might find that you have done something untoward, but in reality, nobody has time for that. Nobody has time for that, right? As long as the program doesn't crash, no one's going to catch you doing any shenanigans at all. And the reason is, nobody understands the internals of the program anyway, right? The reverse engineer understands the internals of the program better than the person who wrote the program. Always, always, right? Programmer does not necessarily understand the implications of what they have done. If they did, they'd have your job, right? Other interesting things to note about heaps and the work that we're going to do with them. I'm not going to give you the inline metadata examples because in my experience, you are always better off attacking the program than you are attacking the heap. And one of the reasons for that is glibc implements this. A random programmer implements the program, okay? Over time, because people are constantly working on glibc, they are recognizing the types of attacks that people do, and then they are doing obnoxious things to stop you from doing them. And very often those things remove the benefits of the optimization in the first place, right? So one of the things people will do is say, oh, well, when I unlink that free list, I'll walk the whole thing to make sure it's good. Okay, well, great. So you've taken your optimization that went from ON, and we optimized it to constant time, and now your validation check made it 2N. So great, what's the point of that, right? But sometimes they'll do that, and that means that you can't perform the unlink trick that you spent however many years perfecting, right?
Speaking of the unlink trick, is that AV09 is just the unlink plug?
Yep. Yeah, it's just an unlink. The other reason that I like that, so the reasons I like it, and the reason that I don't like that particular example. So that particular example, I have 10 minutes, but this is important. That particular example is just a straight heap overflow. So it allocates two chunks next to each other. Two chunks, and you write from one into the other. Boom, 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 boom. And on the way, you smack the metadata that lives right here. And then you call free on this chunk. So you control the metadata, and you control how the allocator is going to work, right? And so the trick is, I want to cause an unlink to occur in an arbitrary fashion. I make another free chunk. I make a fake object that lives here inside the thing I'm about to free with my overflow, and I manipulate how that allocator is going to do the unlink, right? So I don't have to walk to get there. I have the pointer.
Is the fake free chunk in the second chunk? Or
Yes, yep, it's in the second chunk.
Why is it not in the first one?
Well, because you don't have control over the header of the first chunk.
But do you have control of the prev size field for the second one?
You do, yep. So you could say, okay, I'll put it, put a prev size there. So you could, I know there's a reason you generally don't do that. I'm going to have to think about why it is. Yeah, I'll figure it out later. Generally, what you do is you put it in the second one. Right?
How are you going to call free on the address of the second?
You don't. You call free on the address of the first one. The second one is marked free by you because you created the header. So it doesn't actually free the second one. It says, I freed the first one. The next chunk is also free. Let me consolidate them. Now I have to remove the second chunk from there. I control the full header of the second chunk because it's fake, right? It's like a two-level game, right?
I thought it was, because it calls, oh, well, I guess just for this specific example, but it does call free on the second chunk directly, just right after the gets. So.
No, it calls free on the first chunk directly after the gets. So, okay, so the second chunk is not the big chunk. You've overflowed into this chunk. This is the second chunk. You free it. That second free is just there to give you a target for your right what where.
I know.
Yeah. Yeah. But it's calling the one it is freeing the one you overflowed the header of.
Yeah, so when you overflow the header, you call free. Free does the unlink thing where it like checks back, and then when it calls it again, it just, okay, yeah, no.
Yeah, you use that free as a global offset table, right?
Yeah,
That's why I
yeah,
said
yeah.
Here's why I don't like this example. One, it's great for you to understand creating fake chunks and working with that algorithm and doing the reverse engineering. It is not, in any sense, a realistic situation. There is no reason or any time that someone will call malloc just once with a static value in a program. That defeats the purpose of calling malloc in the first place. If you knew how much memory you're going to use at runtime, you'd put it on the stack or something like that, right? The real crux of working with the heap is the fact that you are working with a system that starts in an unknown state. And it's moving in an unknown way, right? When I interact with the program that I'm owning, it's been running a while. People have been using it. I don't know what the heap looks like. I don't know how many pages there are. I don't know what the free lists look like. I don't know anything about it, okay? I also don't know, while I'm doing my manipulations, generally I have no idea what else this thing is doing, right? Somebody here, one of their projects is looking at Wireshark. Wireshark is really hard to own, and it's not because it doesn't have any bugs, it has a shit ton of bugs. It's hard to own because it's always looking at the network traffic and interpreting it, which means it's constantly allocating and freeing, constantly, which means that you getting it into a state that makes sense relies on it not having a lot of network traffic. Otherwise, it's just constantly screwing up the work you've done, right? That's what makes it hard. And that is not present in any toy examples because that relies on you having a program that makes sense that people would use, right? It's, once again, why I don't like people getting stuck in CTFs. You are learning scenarios that are not realistic, and what you need to be doing is understanding common realistic scenarios and how they interact, right? Because there are commonalities between common actual programs because of how people work with them. Cool. All right, so that puts us just about at class end. Does anybody have any questions here that they haven't brought up yet, or about the final project, or about the homework, which everyone has started, correct? Everyone started the homework? You did?
Could you show the code that you're talking about, like that example?
The Apr01 example? Yeah.
As soon as I clip my hair into this thing.
Yeah, so we allocate twice. We have a heap overflow in the first chunk. We free the second chunk that we overflow into, and then we free it. Now, this makes a big assumption here. What's the assumption?
Two static heap allocations, like
It assumes that something about those two allocations.
That they're next to each other?
Yes, that they are concurrent, which is not necessarily the case. I could compile this with a libc that will make a bunch of allocations and frees before this happens, and then when you run this, they're not concurrent, things are possible.
Shouldn't it only, pbuf1 only has to be at a lower memory address than pbuf2? They don't necessarily have to be adjacent, right?
Correct, yep. Yeah, that's true. Yep. However, if that's the case, you don't know how far to write. which means it would still be theoretically doable, but probably not realistic.
We also have to